Welcome back to Honors Calculus. In this video, we're going to be looking at transformations of graphs. The idea here is going to be to find a way to take a known graph of a known function, or possibly a known graph of an unknown function, y equals f of x, and find a way to relate that to a graph of a different function if we can find a way to write them with respect to one another. So specifically, we're going to be looking at y equals a times f of bx minus h plus k. This is what we're talking about when we say a transformation of a graph. If we know what the graph of y equals f of x looks like, can we use that information, even if we don't know the function f, to figure out what the more convoluted function looks like? And looking at each of these variables, we call a the amplitude of the function. I've never really found a consistent name for b, but h is going to be the horizontal shift, and k is going to be the vertical shift. Notice here that there's a subtraction sign next to the h. That is important. That is something that is going to make a significant difference in how we approach our graphing. But the amplitude, a out here, is the vertical stretch factor. And b, the thing that I said didn't really have a name, is the horizontal compression factor. Horizontal shift and vertical shift, I think, are a little bit self-apparent. Right? So let's take a look at what that looks like in graphing. So I have here a function y equals f of x, and the information as to what this function actually is completely hidden from view. Depending on your ability of color vision, if it's better than mine, you might be able to see this clearly. But I have a dashed function y equals f of x and a solid graph of y equals a times f of bx minus h plus k, all of the transformations we've talked about. If we set a equal to 1, and we set b equal to 1, and we set h equal to 0, and we set k equal to 0, these are the exact same equation. And if I scroll down just a little bit in my window here, you will see that that is exactly what I did. And yes, I have a mystery function hiding down there at the very bottom. But there, that gives us everything and some control on it. So one of the things I love about Desmos is when we set some parameters like this, it gives us slide bars. So we can grab the slide bar and we can move that value. So if we have an a smaller than 1, you can see that the amplitude becomes smaller than what it was originally. If we have a larger value of a, you can see that it starts to grow, and it grows fairly rapidly in the stretch that I gave it. Sometimes the boring case, but also kind of an interesting case. If I take a all the way around down until a is equal to 0, the function flatlines. And then if I keep going and I go into the negative range, it springs back, but it springs back backwards of how it was before. It's a little bit difficult to see in this particular function because I'm graphing here an odd function, a function with odd symmetry, which means it looks the same whether you mirror it across the x-axis or across the y-axis. But we did mirror this function across the x-axis. So we flipped it upside down, not left-right. And other than that, right, if we set this to exactly -1, you get the exact mirror of what we had before, and you can keep growing if you want to. All right, let's take that back where it started. B, I said, was the horizontal compression factor. So if we squeeze this down, we get something that becomes narrower and narrower with bigger values of B. And if I had chosen instead to go for smaller values of B, it would spread out once it gets smaller than 1, and it will keep spreading out. And for simplicity, you can see that I've set this up to not be able to go to the negatives because we've already dealt with that with the A case, and it's generally not that interesting to have B become a negative value. H is the horizontal translation. Remember that there's a subtraction sign in the definition of the equation that I'm graphing. And because of that subtraction sign, if I make H a positive number, it slides to the right. If I slide my slider to the left, the function slides to the left. And K will let me slide down and up. So if you have a function that you care about and you want to play around with what the transformations would look like, you can use Desmos to your advantage in that regard. It does play around with a lot of those sorts of things very nicely. Jumping back to our notes page, let's see what that looks like in action. One of the functions that we looked at in our original situation. Hey, I'm on the screen. I wasn't supposed to be on the screen. That's okay. One of the functions that we looked at in our original look at real valued functions was the squaring function, y equals x squared. And among other things, that gave us a nice table of values for that function. And since we have that information, we can use that to our advantage if I want to graph something like y equals 3 times x minus 1 squared plus 2. Now I have to get my head out of the way. I have seen a number of different ways of thinking about how to set up this transformation. They all give us the same thing at the end. But I'm going to draw this table that's going to have several columns in it. And what I noticed right away is that the thing I'm squaring, instead of just being x, is now x minus 1. So I'm going to put in an x minus 1 column, and I'm going to copy down exactly the values that show up in the x column in the original graph. And then I'm going to introduce a new column, which is going to be labeled as x. And I'm going to ask the question, what value do I have to plug in for x so that x minus 1 is -2? What do I subtract 1 from to get -2? Well, I subtract 1 from -1. I subtract 1 from 0 to get to -1. I subtract 1 from 1 to get to 0. Subtract 1 from 2 to get to 1, and I subtract 1 from 3 to get to 2. Right? That's the way I think about the transformation. Now that I know what my value of x is, I'm going to expand out my thoughts a little bit. And since I've dealt with what's going on inside my operation, I'm going to go ahead and take that operation. Right? X minus 1 squared. For this, I can actually go back to my table because I'm taking the values that I know from my original table and I'm squaring them, which is exactly what my original table does. It's not that difficult to do this calculation again for this particular function, but noticing that it's something that's already written down on the page makes life easier. And now, looking back to my original function, I can finally get my value of y. The way this function is defined, y is, I guess I can write this a little bit more neatly. Right? I'm going to be looking at y here, and y is defined as 3 times the thing that I have named blue box plus 2. So I take the value that I called blue box, 4 in the first case. I multiply times 3, which gives me 12. I add 2, which gives me 14. 3 times 1 is 3 plus 2 is 5. 3 times 0 is 0 plus 2 is 2. 3 times 1 is 3 plus 2 is 5. 3 times 4 is 12 plus 2 is 14. And so if you look at just the 2 yellow columns, that gives me the x value and the y value that I need to plot in order to graph this thing. It's going to be a little bit difficult to get everything on the screen at once, so I'm not even going to try. But I'm going to plot the points -1, 14, 0, 5, 1, 2, 2, 5, and 3, 14. Yes, that's the end of my page, so I might be able to get this all on the screen at once if I get really lucky. That's a horrible x-axis. Let's try that again. Right, there's my x-axis, there's my y-axis. I'll count my y values by 2. I'll count my x values by 1. And I'll switch away from yellow and maybe blue to plot these points. So -1, 14 is way up here. 0, 5 is right there. 1, 2 is right here. 2, 5 is about there. And 3, 14 is over here. Play a game of connect the dots. And we have a transformed parabola. Another interesting thing that happens with transformations shows up in our periodic functions. So a periodic function, and for historic reasons, when we talk about the period of a function, we usually use the Greek letter tau. which kind of is pi, but with one leg instead of two. But a periodic function with period tau is any function where f of x is equal to f of x plus tau. That's pi, not tau. That's tau. For every value of x. And the classic periodic functions are sine and cosine. Right? Cosine of x is equal to cosine of x plus 2 pi. To see what I'm talking about, let's jump back over to Desmos. And you can see here that I have, it's somewhat hidden, but in blue, there is cosine of x. And in orange, I have cosine of x plus, I used capital T here, and a slider for the value of t. So I can slide. These look like horrible decimal numbers, but that's pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi gets us back to where we started. But the interesting thing is if I keep going, I'll get to the exact same place again. So a function that has a period of 2 pi also has a period of 4 pi and also has a period of 6 pi and 8 pi and so on. In general, if f of x has period tau, then it also has period 2 times tau, 3 times tau, 4 times tau, and so on. Our convention when we're talking about the period of a function is to name the smallest positive period that we can. So for sine and cosine, the period is 2 pi. For tangent, it actually turns out that the period is pi. And for secant, the period is 2 pi again. So for example, if I have to determine the period of the function f of x equals sine of 3x, well, I can use what I know to my advantage. Because I don't know the period of sine of 3x, but I do know the period of sine of x is 2 pi. So sine of 3x is the same thing as sine of 3x plus 2 pi. And I might have to get a little bit creative, but notice here that I can factor, and this is 3 times the quantity x plus 2 pi over 3. But if you think about the original definition on the first line of this derivation, f of x is sine of 3x. So sine of 3 times x plus 2 pi over 3 is exactly what you would get if you tried to evaluate f of x plus 2 pi over 3. And so we take x, we add 2 pi over 3 to it, we get back to where we started, no matter what the value of x is. F of x has period 2 pi over 3. The fact that there is a 3 here and a 3 there actually is not a coincidence. In general, the period of f of x equals sine of some arbitrary b times x is 2 pi over b for any constant b except 0. Right? Sine of 0 times x is very boring, and we just won't talk about it. And that's what I want you to look at for this video. Instead of looking at how to find the period of a particular function like we just did, I'd like you to think about how to prove that this works in general. If you know nothing about a function other than, or you know nothing about the value of b, you know that your function is given as sine of some b times x, then the period of that function is 2 pi divided by b. All right, to think about what a proof looks like, think about how to show that that's going to hold in general, and I'll see you in the next video.